An EC fan in a semiconductor cleanroom is not simply moving air. It is defending a particle-sensitive process boundary. If one fan filter unit slows down, a filter loads unevenly, or maintenance opens the wrong side of the ceiling, the cleanroom can still look normal while the airflow pattern around the wafer has already changed. So the useful question is not, how much air does this fan move? It is, how does the complete FFU system protect the process in every operating state? Start with the air path. Conditioned air enters the ceiling plenum, an EC fan draws it through the FFU, the final filter removes particles, and the supply face distributes clean air into the process bay. Air then travels past the tools and people, into the low return path, and back to the air handling system. The critical point is the wafer or open process zone, not the center of an empty room. That is why a semiconductor facility is better understood as a map of contamination risk. A ballroom cleanroom, a localized clean zone, and a mini environment can require different protection boundaries. The fan strategy must follow the owner's cleanliness requirement, the process layout, heat release, return air architecture, and the room state. Do not copy a universal velocity, air change rate, or ceiling coverage from another project. The FFU itself is a series system: inlet condition, fan, housing, filter, diffuser, and room return. When the filter is clean, the fan sees one resistance. As particles accumulate, resistance rises. If the controller holds only a fixed speed, airflow can fall. If the project requires regulated airflow or pressure, the EC fan, sensor location, control loop, and alarm limits must be engineered and commissioned together. EC describes the motor and control platform. It does not guarantee a constant room condition by itself. Now look at uniformity. One average room reading can hide a weak ceiling module, a blocked return, leakage around a filter, or turbulence from process equipment. Map supply airflow or velocity across the ceiling and inspect the path to the critical zone. The correct acceptance method depends on the specified room and airflow type. The objective is repeatable protection where the process is vulnerable, not a visually impressive average. This is a real Longwell FFU product view. It confirms the physical architecture: compact ceiling modules with a fan inlet above and a filter face below. It does not, by itself, prove semiconductor performance. That proof comes from project-specific filter resistance, airflow, pressure, electrical input, sound, control behavior, installation details, and field testing. EC fans are valuable because speed can be commanded and operating status can be monitored. A robust schedule defines enable, speed or airflow command, feedback, alarm, communications, and failsafe behavior. It also says what happens after a power interruption, a lost sensor, a communication failure, or an FFU fault. A dashboard is useful only when the physical response behind each status point has been tested. Redundancy also has to be spatial. If one ceiling module stops, neighboring units may compensate, but the resulting flow field can shift. Check the module out condition at the protected zone. Consider reverse leakage through an idle unit, common power feeds, shared controllers, and whether one maintenance action can disable an entire bay. N+1 on a quantity list is not the same as verified process protection. Maintenance is part of contamination control. Decide whether the motor, electronics, and filter are accessed from the ceiling side or the cleanroom side. Define isolation, lockout, filter handling, tools, temporary barriers, cleaning, and recovery testing. A module that saves a few minutes during selection but spreads particles during service is not a good cleanroom solution. Energy still matters because every watt delivered to an FFU ultimately becomes heat that the facility must remove. Evaluate measured electrical input over real operating modes, including clean and loaded filters, reduced production, recovery, and fault conditions. Optimize the system while maintaining the required cleanliness performance. A lower fan speed is not an energy success if it weakens the process boundary. Commissioning closes the loop. Depending on the project, the evidence package can include filter integrity, airflow volume and uniformity, room pressure, airborne particle concentration, recovery, sound, vibration, electrical input, controls, and alarms. Record the room state as built, at rest, or operational, because results from different states are not interchangeable. For an FFU fan review, send the required cleanliness condition and room state, module size, airflow, clean and loaded filter resistance, voltage, control protocol, sealing grid, return path, sound target, maintenance side, and fault philosophy. Then the fan, filter, controls and cleanroom boundary can be evaluated as one system. For a project-specific review, visit longwellfans.com/contact.